record and share screen. Okay. Share screen, share screen. Okay. Okay, I'll use this material in Latvian, but basically I need pictures to discuss some power system control aspects. First of all, let's simplify power system to a united generator, some transmission lines, and a load. So we'll use mainly three units. Yes, generation, transmission, and consumption. Yeah, to simplify. Here we could see the scheme for a hydropower plant. Yeah, so we see the water flow, we see the turbine and the generator. And here is a schematic how this type of generation could work. So if we concentrate, if you unite all generators to one, the first question is how this united generator could look like. Because, for example, we have different types of generators. We have hydro, we have some solar, wind, when we have inverters. Yes, we have turbo generators, and they are different. And the main question is how, if you unite all the generators to one, how this one generator could look like. Yeah, this is a quite complicated question, and the easiest way, if we could group all the generators, yeah, by the type of generation. So, for example, we unite all hydro, we unite all turbo, we unite all sources that use inverters, yeah, DC sources, yes, and use all these types. But to start, we use simplest model as possible with one generator, for example, hydro or turbo. Yes, there is, for this schematic, there is no much difference. So let's look inside. First of all, what do we see here? Okay, I'll translate all these words. It's easier. We don't have a lot of things here. First of all, we have here the power system. Yeah, power system block that contains consumption, consumers, loads, and everything else that is in parallel. Yeah, this one is the control unit block. Yeah, this is generator. Yes, our generator that produces electricity. So this is power network, power system. We produce electricity and transfer this electricity to the network where we have all the transmission lines and consumption. Yes, this is a control system, and this is how we transfer energy, mechanical energy, yes, to the electricity. If we use this hydro type of generator, yes, what do we have? We have water, we have valve to control the water flow, and we have the turbine, yeah, water turbine. So here we have the block of turbine. This one is valve, this one is water. So water, valve, turbine, turbine rotates generator. This is control system. This is rotating speed measurement. This is rotating speed regulator. And this is the information from the turbine. This is turbine rotation speed, real rotation speed. So what we got? We open the valve, water goes to the turbine. Turbine starts to rotate. Turbine is rotating and moving the generator. Generator produces electricity. Here we got the information about the turbine rotating speed. This rotating speed comes to the rotating regulator, to rotating speed regulator, yes, to control all the time the rotating speed to be constant, yes, because based on the load, yes, if load increases, it means we need more power, it is more difficult to generate. For generator, it means we need more power. A power, mechanical power, is water flow. So we need more water, more pressure to rotate the generator. That's why if we have more, if we have higher consumption, bigger consumption, yeah, it means that rotation speed comes down, yes, start to rotate slowly. We need more water, we need to open the valve, we need to measure the rotation speed and to make the control signal to make more water flow. Now this is the simple schematic, yes? This is control, yeah? This is the part that converts all the signals, so the main part is here. In this case, we could convert this scheme to the control theory block scheme. So using the control theory, yes, using these transfer functions from math, yes, it's control theory. It's also, okay. It's part of it. Uses a transfer function from math, yes, to make the regulator. So we could transfer this one to this one, and next we'll discuss all these transfer function. I think this information should be known for you, but we'll repeat. For today, we continue this overall view for the power system, how it works, how it operates, and how we could model this power system with control. This is how to say the first look to this. Okay, so in case we have this schematic. And what we could see here, we see that we have information about the power system, about what's going on in power system. And we have the control of the generator, yeah? If we need to produce more power or if we need to produce less power. How we know what's going on in power system? No, first, from this scheme, it is quite clear what the rotating speed. In other words, rotating speed is the same as a frequency, as it was mentioned in previous lecture. Yes, the frequency, voltage frequency in our network. What is the frequency? It's similar as a rotating speed, because rotating speed, what does it mean? How much this rotates per minute? What is the frequency? The same. So these parameters are not equal, but they show the same. That's why the most important parameter about the situation, about this power balancing, what is going on in the power system, is a frequency. Do we have enough power for load or not? Okay, so we need to keep this balance all the time, but situation, normal live operation, we have a disbalance, yes? Is it dangerous? The first question. And the second question, how much time do we have to do any actions, yes, to restore the balance? And this is quite important question. The first one, is it dangerous? Yes. If we operate if we operate with the frequency not equal to the standard, to the nominal value, for us it's 50 hertz, yes, it is dangerous. Dangerous for power system elements, such as generators, loads, and so on. That's why it is very important to keep this frequency like a nominal. But the first question in this case could be, what is the possible deviation for frequency? What frequency is good? What frequency is dangerous? And for here, for example, okay, of course, this will be a little bit next, but I can show you one interesting picture for now. This should be okay. Yes, it is here. I'll show you these pictures. This picture is about the turbo generator and the frequency. So what time the turbo generator could operate with different frequency deviation? Because as it is dangerous, it means that we have a protection for this generator, and the protection will disconnect this generator from the network in case, yes, if the frequency is not nominal and the operation condition is dangerous. Okay, so as it was told, the nominal for this generator is 50 hertz, and here we have the time. Yes, here we have frequency, here we have the time, yes. And what we could see that, for example, if we have decreased frequency, for example, 47 hertz, we have only 20 seconds of possible operation. Yes, if this frequency keeps for more than 20 seconds, protection will disconnect this aggregator. Of course, if we have such protection, for example, for generators, of course, we have such type of protection because they're very expensive, a very valuable part of the power network. But for example, for loads, yes, for load, this is dangerous as well, but how to say, who cares what's going on with a load, yeah? Of course, if you don't know any huge manufacturer, you have your own lawyers, you can prove that the frequency was wrong and so on. Of course, for the network, for the utility company, as a result, this could be very expensive. Yes, all their losses due to this abnormal frequency and a normal regime. Yeah, but to understand, this is just a brief view, yeah, that the frequency, when it is not nominal, we have not much time to do any actions, yes, to restore the frequency. For example, this with a value of 48, we have only 60 seconds, yes, possible operation. And one more very important information, okay, very briefly, I need to find, is it here or not? I just need to show you some values. Yes, for possible, this is some values, some values. Okay, maybe not here. This is there. No, maybe okay. Not here, maybe here. Very briefly, but somewhere. Here as well. Yeah, here I found this. Okay, here I found this is this ends to im. This is European regulation. Yeah, how the operation should be organized, and here we give some very important values. Okay, about the frequency, the values, yeah? So what is a nominal? Nominal is a frequency plus minus 50, yes, millihertz. When it is unnormal, when the deviation, yes, is more than 50 and less than 150. And if the deviation is of frequency, if it is more than 150, yes, this is a huge deviation. So that means that we are far away from the nominal and we need to make any action to move it back. So this is normal, this is unnormal, but this is dangerous. We need, of course, in this case, yes, we start to do something. But this deviation is small and it is quite easy to return to the nominal value. And if it deviation is more than 150 millihertz, yes, you see, that means that we have a huge deviation. And this becomes dangerous, yes? This is how it is important. This is standard regulation for standard regulation. But we'll discuss in details a little bit later. Today we need to continue our brief review about this power system construction. Okay, so I need to come back to the number four. Okay, yes. Okay, so now it is clear that frequency deviation is very important and dangerous. Deviation means that we don't have the balance in a system. I show you the screen about, for example, how much time do we have to do any actions for the generator, yeah, in case of the frequency deviation. And that this is dangerous the same for all power system units. And now the second question that are presented, how much time really do we have to do any action? And first of all, we need to understand the speed of any change or any parameter change in a power network. For example, let's start with the frequency. So if we have this disbalance, we will have the change in the frequency. The question, when or how fast, how quick this deviation could appear. And to answer this question, we need to understand one very simple but very important things from a physics. What is a generator? A generator is a big piece of metal, a big rotating piece of metal. And this means that it has a kinetic energy and inertia as well. So if we have a big rotating piece of metal, it means that it is not so easy, yeah, to change its rotating speed quickly. It means that this kinetic energy, this rotating kinetic energy, this inertia, yes, goes backward, yeah, to the any change in a power network. And this gives to us time to make any action. This why inertia is very important. For example, if we have a network with only with renewables source of energy, it means that we produce DC, we have inverters to convert it to the AC, yes, and inverters push energy to the network. Inverter is not a rotating piece of metal. It means that it doesn't have any inertia. In this case, all the changes in the power network goes very fast, and we don't have any time, yes, to make actions. That's why from the point of view of stability, reliability of power network, renewable sources with inverters are not very good. I say they're bad. But okay, let's come back to this topic. So inertia. Inertia, it is our time to do any actions. But how we could calculate this inertia, how we could understand how much time, for example, this inertia could bring to us, yes, for any action and any operation. Now, let's view inside this question. So this is a again simplified schematic for our review. So here we got the generator, load, turbine regulator, and the valve, yeah, the same as we saw previously, yeah. So but just a part. So we have a turbine, yes, for example, steam turbine or hydro turbine, this regulator of the rotating speed, this mechanical energy, this is electrical moment, yes, of generator, and our load, and control of the valve to give more or less water or steam, whatever, based on the type of generator. And this is equation 4.1. This is n moments. This is the rotating mass, J rotating mass of this metal piece. And the result of all this is here. 4.7 equation, how the inertia looks like. The H letter shows the inertia in megajoule, megavolt amps. But there are two approaches, two ways how we could evaluate the inertia. The first way, this is more popular for West countries, to represent inertia with the energy. And the second way, with this T letter, it is more actual for European East countries. I say for European because I don't know what how it is in another world, to represent this inertia in time, in seconds. And these two values could be represented, so the t time is value 2 multiplied by h. So yes, so if we represented it energy, we could convert to the time just multiplying by 2. Okay, so the idea is the same. The question is how we represent this parameter, yes? For every generator and every single generator, this parameter is known from its technical data, yes? Because it is metal piece, so we could know from this manufacturer, from the technical data, what is the inertia of this single piece of metal. But when we are discussing about the power system, when we have hundreds of generators, we need to understand, to evaluate this power system inertia, not every single generator. How to do this? And we have, this is not a complicated task. This is quite important, but this is quite simple as well, if we, of course, we have information about the every single generator. And here we got the 4.12 formula, how to calculate. No, this formula represents it in time, and for example, here we got the table, when we have for different type of generators, its parameters, just for as example, for and its inertia, I could take J in seconds. So how to calculate the system's inertia if we know the information of every single generator? Quite simple. It is the sum of a single generator inertia multiplied by the every generator its own power divided by the system power, total power. Very simple formula. And here is an example how we could calculate just for a training. So we, for example, we have system from two generators, generator 1, generator 2. The first one is 500 megavolt amps. The second one is 1343 megavolt amps. And we got the inertia of every single, yes, H1 and H2. So let's calculate the total inertia. So using this formula, let's calculate this part for every single. So its own multiplied by its own inertia multiplied by its own power divided by the total system power. Okay, for the total system power, if we have only two generators, means the first one plus the second one, and the result 1833 megavolt amps. So inertia, no, okay, this part. So this part for the first, because it is a sum. Yeah, so H1 multiplied by S1 divided by the S system. So 4.8 multiplied by 500 and divide by 1833. Here we go. And the result 1.41. For the second, so the second generator inertia multiplied by the second generator power divided by the system power. So the second one is 3.27 multiplied by 1333 and divided by 1833. As a result, for the second one is 3.69, and the total, 2.80 or 38, and the total is the sum of these two and is equal to 3.69 megajoule divided by megavolt amperes. So this is true for any number of generators. So if we have a power system when we have hundreds, yes, we need to calculate this inertia, and this value will show us, yes, of course, we need to make a model. We need to make a model. Maybe this such simplified as it is here. And to use this calculated inertia toward this model to analyze, yes, the time of reaction of any disbalance in a system, to plan the operation, yes, to understand how much time do we have, how much balancing power step do we need to do all of this. So, but for today, it is an introduction. So we need to understand these important parameters, what we need to know about this power system. Okay. This is about the inertia. The second topic, what do we need to know more about this generator? Okay. And to control, let's look to this picture. So what do we see here? Here is P, power. This is time. And we have two curves. This curve is rotating speed. And this is the power, mechanical power. And we see the two parameters in time. So when we have the deviation, yeah, about these powers, this is the difference, yes, here and here, this delta, yes, different in a load, yes, in the power, what is going on. And what we see, first of all, we see the difference, yes, about the rotating speed, because this rotating speed is equal to multiple by P and by the frequency. So rotating speed, as you said, they're similar, not equivalent, because they have the difference in 2p, yeah, multiplied by 2p, but they show the same. And the power deviation, you see, we have, first of all, we have the lag of time, yeah, in the process. And second one, we see how they're changing, yes? So we have the different amplitude, of course, and the main what we could see here is this difference in time, yes? That's why, as I said, this inertia is very important. The second thing, okay, about all these schemes we'll discuss next, we'll go through. But the next very important thing, as we see this difference, yes, about the frequency and the power, because if we see the difference in frequency, we need how to convert this deviation to the power deviation to evaluate how much power do we need, more or less, yes, and what actions to do. And here we got this curve called the statism curve. It means that the change in the frequency is equal to the change in power, yes? What change in frequency is equal to the what change in power. Of course, this curve is not a straight line. This curve is very complicated, but as it was shown For example, here we are interesting, yes, to look to the small deviation of frequency around the nominal value, because if the deviation is more, nothing is possible to save, we will have a blackout. So the normal regulation is around this normal value of 50 hertz, and the process around this value, we could simplify this law, no, okay, this dependency, yeah, we could simplify this dependency, this curve, and to use the straight line. So it is a simplification, but this simplification is true, it is possible, and it is easy to use in practice. So yes, we see this, we are interested in deviation around the value of 50 hertz, and this piece of curve we could linearize, yes, and use this straight line. So, and this straight line gives us information, yes, how we need to react, yes, on a frequency deviation. So this curve shows or says to the generator regulator, yes, how much more power do we need to produce if we have the frequency deviation of such value. Okay, well, this is true for one generator, and every regulator of generator that participates, of course, in power balancing in this regulation. Because, for example, we could have a lot of small generator that are just connected in parallel to the power network without any generation regulation. Why? Because it just goes parallel. If frequency in the system rise up, so it starts to rotate faster. So without any regulation, just in parallel. Such types of generators don't participate in this regulation, yes. But as I said, it is important to make these regulations. That's why we are talking about this generator with regulation. Of course, we when we make models, we'll see how what's going on if we have this regulation, if we don't have this type of regulation. But okay, this will be next. For now, it is important, yes, for us to understand how what is dependency on frequency deviation to the power deviation. Okay. And regulators have this curve, instead, this built-in curve, yes, for the control. For the control. And the next important question is this one. This one. If we have this regulation for every single type of generation, but the power, nominal power of every generator is different, any possibilities for every generator to react on frequency deviation is different. But if we want to know what will be the total reaction of all the generators to the frequency deviation, for example, we will drop the frequency for 50 millihertz. It means the generator number 1 will produce more power for 5 megawatts. A generator number 2, because it has more nominal power, will increase the energy production by 10 megawatts, and so on. So the question is, yes, how we could calculate, yes, what will be the because the frequency is the same in every part of the power system. So if we have this imbalance, so we have this deviation, but the reaction of each generator is different. And we need to understand to calculate the total reaction. And here we have the picture, the figure with two generators. So, and here we could see the frequency deviation, yes, in a network, and the power change for generator 1 is delta P1 and delta P2 for the second one. No, this is, I think, is, oh, sorry. This is quite simple, just to show this important moment. And if we make a model with concentrated generator, as I mentioned many times, yes, when we unite all the generators to the one, we need to represent this reaction, yes, on the frequency deviation, yes, by the united generator, how this could be done. And in this case, we need any possible formulas to calculate what will be the total reaction of united generator. And here we got this formula. Here we got this formula. For example, this is delta P, so this is different, the reaction for the first one, which is equal to this frequency deviation divided by the nominal frequency multiplied by the nominal power of the generator, and it's this curve, yes, called the statism, and it represents with a coefficient K. Why it represents? Because no, it is simple from the school math. When we have a straight line, yeah, we could represent this line by the coefficient. Or maybe I'll just remind. Okay, very simple. From a school. Okay, we have. And we have, for example, line. Okay. What is the formula? Oops. What is the formula of this line? Is kx. Y is equal kx. Yes, this is from school math. So, and with this k coefficient, yes, we represent this statism straight curve. So K1 this curve and K2 this curve. So as it's clear, the total difference in power is equal to this delta P1 plus delta P2, yes. And if we need to calculate this curve, yes, this curve for the united generator, this formula is how it calculates. And if you want to calculate the deviation, the total deviation, for example, of every single, here are the all possible ways how we could use this formula. Yes, if you know to calculate this statisms for united generator, the formula is here. Or if we have this united, or no, if we don't have this known this deviation, but we have only statism, we could calculate it. But the main thing, yes, what I want to say is formula this, yes. So when we have this united, we could calculate this united generator statisms, and based on this united statisms, we could calculate united deviation in power when we have the frequency deviation. Okay, this is the second important thing. The third for today, so here we got the generator reaction on the frequency deviation, but we have an opposite part of a power system, user, consumer. when we have the frequency deviation, the frequency drop, it means that we provide less doses of energy per minute to the end consumer. It means that the power density is decreasing, and it means that the consumer will not receive as much power as it is needed. For this case, we have the same way how we could calculate the reaction of a consumer of a load, of a rotating load, of an electrical motor, when we have the frequency drop. And here we got the same, because as we understand, this generator is rotating machine steel unit, yes, and the electrical motor is the same rotating machine. The difference, one produces, the second consumes, yes. So that's why the idea is very similar, and the formula how we could calculate the reaction is very similar as well. So the reaction for the load, the frequency deviation divided by the power deviation, that is equal frequency deviation divided by the nominal frequency multiplied by the nominal power of the load divided by the power difference. So how less power will receive yet the load when we have drop of frequency. So this is the third very important part for the modeling. So inertia, the time of reaction, statisms, regulation, of the generator, and statisms, the reaction for the load. What is very important? Okay, so okay, done. We have time, and that's why we could go to the next question for today. The next big question is, the next one is about what to do. Now we have discussed about the frequency drop, the power balancing, and the reaction of all of this. The next question is, what could we do if we don't have enough power to restore the balance? In this case, we have special under-frequency automation to save the power system from a blackout. It is clear that if we don't have generation power, it means that we can't produce more. But we need to keep balance to save the power system. What to do? If we can't produce more, it means that we need to disconnect the load. The last chance is to disconnect the load to restore the balance. And here, for example, we have very interesting figure about the speed of frequency drop in case of different shortage of power. This is a shortage of power in a power system, 10%, 30%, 50%, 100%, yes? And the speed of frequency decrease in such power. Should be mentioned that here we don't have any regulation So we don't have this any additional power from generators. This is just a figure to show the speed, yes, of frequency decrease. Of course, here we could see different curves for every color. Why? Because, as I said, the inertia could be different. Inertia have the impact of this for the speed. That's why there are several curves with same color to show this difference. Yeah. But the main idea of this feature is, yes, to show what is the difference in the drop speed, yes, with different shortage. How fast, yes, could this frequency decrease? Okay, so as I mentioned, to save the system, if we don't have enough power from generator, first of all, the first reaction, and next lecture we'll discuss all these primary, secondary, and types of power regulation. Yet rules about how we could regulate all of this. But if we don't have enough power in the system, all these regulations are useless. Of course, on this score, on this figure, we could see the reaction of regulation. So this the increase of frequency or the decrease of the drop. Yeah, it depends on the shortage. But the main idea is, yes, that if we don't have enough power, the only way to save is to use this under frequency automation to disconnect the load. I want just first of all to show you some good figures. Not here, not here. I think I need to show you from here. Because good figure helps to understand this from another source. Same topic, but another source. Okay, yes, this picture, this nice picture. This now picture, very nice picture, the idea of under frequency automation. And first of all, here it not because it is in Latvian, yes, it calls AAF under frequency automation. There are two parts of such automation. And this is very important to describe the difference of these two ideas. First of all, two types of under frequency automation was developed in Soviet Union, and still they use such system in Russia and post-Soviet countries. In Western countries, they don't have this separation for this under frequency automation 1 and under frequency automation 2. And in next lectures, using the historical report about this several blackouts in Europe, we'll see the difference in philosophy, how to use this under frequency automation. In this scheme, we have all these two types of under frequency automation for the understanding the idea. Now I'll try to explain. First of all, here we got the frequency, nominal frequency. We have any trouble in system, any fault, and we have this deviation, so the drop of frequency. The drop of frequency. Under frequency automation have a special set point, frequency level set point, to understand that we have problems. Regulators can deal with this, and we need to disconnect the load. So this is F and O, means this the set point for the load disconnection. And we have several such set points. So it means that when the frequency decreased to a set point level, the dose of loads will be disconnected. And the number of these, how to say, set points could be different. What is the idea of such use of load disconnection? First of all, the system automation don't know what is the shortage of the energy, because as I mentioned, yes, the difference in frequency not so easy to convert to a power. We need a model to do this, very in a details, a complicated model. And if we with one step could disconnect the right value of a load, yes, this could be very good. But due to this is quite complicated, and to disconnect more when it is needed is not good, yes, because people, enterprises, yes, will be disconnected from the network. All of this is economical losses, so this is not good. That's why trying to disconnect with the doses, yes, of the loads. So if disconnect, you see, for example, this process starts here, point B, disconnect some load, and you see the load is decreased. So that means that imbalance is decreased. So the speed of frequency drop is decreased as well. But it is still continue to decrease, goes down, and it means the next dose of load will be disconnected, and so on. So here we got the curve 1, 4, 5, 6. They are here to show that with different inertia there is a different speed of frequency drop. With the same shortage and the different inertia, the speed is different. So that is a idea of the under frequency automation, yes, to disconnect the load until there will be the balance between the generation and the load. But there is a big negative moment. Here you could see, for example, point number 5, yes, here, yeah, we have the system in balance. So we have disconnected enough load to restore the balance between the generation and the load. But we are with the frequency far away from the nominal. We have the balance, but frequency value is not nominal. That's a problem. To deal with this lower frequency when the system is back to the balance, that's why there is a second type of under frequency automation. Here it is. And this is example from the point number J. So we are in balance, but system after some time, because the second type of under frequency automation starts with the time set point. Continue to disconnect load to make the power, the production more than the load, to increase the frequency to the nominal value, if of course it is possible, if we have enough possibilities to disconnect the load. So it means that automatically, without the human impact, yes, not to restore the balance, but to restore the nominal frequency as well. So this is a philosophy. In Western countries, under frequency automation stops working when the system is in balance. And to restore the frequency is a human operator task. What is not very good? Why? Because human in these, how to say, emergency systems could do a lot of mistakes, and of course human speed, the reaction speed and so on is much lower than the automatic. Automatic will do this without, how to say, any stress, just using the algorithm. In this case, I think that the second under frequency automation must be in every power system. But in Western countries, there is only this type of under frequency automation, and as a result, we will see we have different blackouts that could not be happen if there were a second type of under frequency automation. Okay, so this is about the idea, how it works. Let's see, look into some formulas. Okay, about this under frequency automation, about the structure. First of all, it is important to understand, for example, how much load do we need to connect to the under frequency automation? Yes. What type of loads could be disconnected in this emergency case? And how to plan, how to organize this disconnection. For example, how much steps for this, how much set points do we need, how much steps, yes, and how much loads should be connected to every step. For example, for Latvia, we have a very reliable power system, one of the most reliable power system in the world. Historically, it was developed using a lot of different experience, and it is very reliable. That's why we don't have an experience with under frequency automation. We don't have statistic data. That's why we have all the same stages here. So we don't know how to connect, for example, how much load would be better to connect to the third, second, third, and so on stages, because we don't have historical data of such problems. That's why we have n number, it is about 18 number of stages here, yes, of set points, and every set point has the same power, load power, yeah, for disconnection. In different countries, yes, they have different experience, of course, negative experience, and they have different structure, how this works. Here I can see, for example, so different, so it's Examples, for example, it is for this Portuguese, yes, when the frequency drops to the 89, or sorry, 49 hertz, 50.6% of the load must be disconnected immediately. And with the same value, same set point of frequency, with the next step and time delay 150 milliseconds, 80%, 18% more, and with times delay 500 milliseconds, 0.7% more. Why so strange? Because we have an experience different. I think it's based on the why transition capacity lost by generation loss based on their experience. So such values for disconnection and this for how to say smooth regulation. Yes. The same is here. The second step is when the frequency drops to the 48.8 hertz. So 3.9% of loads of connected should be highlighted. This percent is 3.9% of connected load to the under frequency automation, not from the total load of the power system, but over 3.9% of load that is connected to the under frequency automation. And the question is, yeah, how much power of load power do we need to connect to the under frequency automation? But we'll discuss this question, I think, next. Next step, next. Okay, this is, for example, for Portuguese. For Portuguese. For example, here for... Okay. No, for example, for this is for Israel. Yeah, this is the number of this is stage number. These are set points, and these are loads. This is in not percent but in values. These are in percentage, but additional important information. Yeah, additional set point. Not only the frequency value, but the frequency change speed, how fast frequency is changing. Yes, this is additional set point for activation of a set point. Yeah, this is interesting. Okay, so come back to the formulas. And what we got here. Okay, the first question is, for example, we have okay, I think we need to start with this 4.6 and 4.7 formulas, because very important for us to understand the power of the load that we need to connect to this under frequency automation. And to answer this question, first of all, we need to set what is the minimal possible frequency for our power system, not to, how to say, allow the blackout. Yes. And here is F minimal. This is informal. This is, we decide what is the possible minimal frequency. And based on this possible minimal frequency, we could calculate the power that should be connected. Okay, what we got is this informal. This is the possible deficit. This is the nominal load power. This is nominal frequency. This is minimal possible frequency. And this is, as I said, the load reaction. Load reaction, as I mentioned today, to the frequency drop. And using this formula, we could understand what is possible, what could be the possible frequency connected to the AAF automation. In this case, there are two types of AAF automation. That's we could ask the second question. The first question, what is the minimal possible frequency? And we calculate this. And the second one, yes. And the second one is how much power do we need to connect to the second type of automation to restore the frequency. And this is FATJ is the value of restored frequency, yes? This is formula 4.9. Okay, and some summaries that usually to the anti-frequency automation first type is connected about 30-50% of the total load, and to the second type of anti-frequency automation is about 12-20%. Okay, I think this is enough for today, as we agreed that we have only one lecture per week. So the next time we'll practice some tasks for practice, because we have different formulas for inertia, for statism, and for anti-frequency automation. We try some practical tasks. Next, we will investigate some blackouts in Europe. Then we discuss a little bit basics of control theory for modeling, and then we'll start to make models in MATLAB for your homework. Okay, that's enough from my side. Maybe some questions.